Okay, I felt that perhaps we should talk a little bit more about buffers. So before we actually move on, I just want to talk a little bit more about buffers. And buffers had the HA equation, which was pH equals pKa plus log of base over acid. Okay, there's also another equation. Terrible looking. See? There's another equation for using the pKb, and it involves pOH equaling the pKb plus log of acid over base. Everything is actually just the opposite. All right, but we're going to focus on the first one. And the buffer is resist a change in pH. It resists a change in pH, and if you add, an acid or a base to a buffer, and as long as that acid or base is stronger than the acid or base inside the buffer, then it will totally react, and you'll end up with an adjusted pH, a new pH. Okay, what I mean by that, though, is that you can just subtract the moles of the added acid or base and do a very quick calculation to get the new pH. That might sound a little confusing, but we'll see that a little later in our examples. Okay, a couple questions here. A buffer is made by adding 0.740 moles of H acetate acetic acid to 0.530 moles of sodium acetate to 1 liter of water. What is the pH of this buffer solution? Okay. Well, and I guess this is what I'm going to start off saying right now. These brackets mean molarity, which is moles over liter. Right? This, if I was going to simplify this, it'd be like that. Moles of base over liters, moles of total solution, moles of acid over liters of total solution. The moles are different in most cases. The liters, though, because it's in the same, the solutions are the same. It's the same liquid. Okay, so the liters will always be the same. Okay, so they get crossed out. All right. The reason why I'm mentioning this is a lot of times when we start adding solutions in solution stoichiometry, things get a little peculiar, things get a little bit more difficult to see because of the added volume element. Okay, you have to account for the added volume, and then life gets a little bit more difficult. All right, you have to adjust the equation for the additive of the the extra solution that's coming into play. But the equation will work with just moles itself, so we don't really have to worry about the volume. So whenever you're using Henderson-Hasselbalch equation like this, it becomes more powerful when you use it in moles, because you'll see, and sometimes you have to do some adjustments if you're going to do it in molarity, and it creates just a lot of work to come up with new molarities of both the acid and base, where you could actually just use moles instead. All right, so they give us moles, so we're just going to use moles. If you remember, the pKa of acetic acid, which is 1.8 times 10 to the negative 5, is 4.74 plus log. All right, base comes first, which is 0.530 over acid. We don't have to do much labeling on something like this. What you would actually do is write the equation, the expression, without anything in front of it, and then it's just a plug and chug from there. Doing my math on this very quickly, I'm going to see that I have 0.53. I have a pH of 4.60. All right, wrong end. 4.60. 4.60. That's my new pH, or the pH of the buffer. Okay. So if we did this in icebox, it would take a little bit more time, probably 2 or 3 times more time. It'd still be a fairly quick process, but much, much quicker. Just do it this way with the HA equation, Henderson-Hasselbalch. All right, now what's going to be the pH after we add our strong base, our sodium hydroxide? And you can see what I'm getting at here with this whole idea of additive volumes. I have to take into account that the volumes of everything's changing, because I have this whole idea of adding a volume to my volume of 1 liter. So I'm going to have 1.6 liters and things of that nature. So using this system here of just moles over moles is very important. So my new pH is going to be 4.74 plus, okay, the log of, well, how many moles of base do I actually have here? 0.180. Okay, so this is 0.180. And since this is less than the acid that I have, I can just do subtraction here. Okay, so what I'm saying is, because I'm adding a base, it consumes the acid. So my acid was 0.74 moles, but now it's going to be subtracting the 0.80. I'm sorry, 0.180. And on the flip side here, the base is going to get larger. So because I'm adding base, and remember what this is, it's a buffer. So my NaOH, because it's a buffer in the reaction there of neutralizing with with the H's and being replaced to create more acetate. I'm adding OH, but I'm actually just adding acetate ion. Which acetate ion am I adding? I'm adding this acetate ion, this much. So I add it to the top. And plugging these into my calculator, small adjustment, 0.474 plus log. Okay, getting a little crazy here, some parentheses. I'm adding to the top, and I'm subtracting from the bottom. And I get a new pH of 4.84. Okay, well, it makes sense. We added a base, and look what happened. Our pH increased. It went more basic. But not by very much. Okay, not by very much, and not by very much because, remember, this is what a buffer does. We're adding a strong hydroxide, a strong base, but the pH actually did not increase by that much. Okay, so this is a good example of actually showing exactly what the buffer does. And it's all about, if you add H, it turns into the weak acid. Okay, H plus is super, super strong. Okay, it's pure acid in a sense, pure hydrogen ion. But when you add H plus, it actually turns into acetic acid, the weak acid. If you add OH, the super strong base, it turns into acetate ion. Okay, so all you have to do, this is the stoichiometry right here of what's actually happening here, is the plus minus. Okay, here's where these can get a little bit more fun. Next problem. Using the initial buffer, okay, so I'm just going back up to this math. How many milliliters of 0.600 molar NaOH must be added to get a solution with a pH of 5.73? Okay, so I'm adding base. And I need to know how much base to add. This is a question This is what makes buffers more difficult. Okay, traditionally buffers is about the pinnacle of difficult questions that you receive. We seem to be doing a pretty solid job with it, to be quite honest with you. But this is a typical AP question where they try to limit the words, all right, where it's just raw horsepower to see if you can figure it out or if you remember doing a problem like this. Okay, so it's up to you to be able to figure out what's going on here. They're asking for a volume of a molarity. It's a little bit awkward. Okay, volume of a molarity. Anytime you're dealing with molarities, okay, you may be better served, just like I said earlier, to just deal with moles. So if I can figure out how many moles of NaOH I need, then I can figure out the volume of NaOH I need. Okay, what I mean by that, this is actually a very simplistic setup. My pH I want is 5.73, and that's going to equal 4.74 plus log, okay, of, we're going back to my original calculation here, the original solution, 0.53 over 0.74, okay, base over acid. And because I'm adding NaOH, I'm going to add base. How much base? That much. And if I'm, the reaction must show the other way as well, that it's consuming acid. How much is it consuming? It's consuming that much, X. All right, once we solve for X, remember what X stands for. X is going to stand for the number of moles of NaOH. Once we solve for X, then we can get this whole business of volume, okay, just by what the definition of molarity is. All right, that's very simplistic. Now we set ourselves up that we can actually just solve this thing for X. And you have a couple options here. All right, you can just use algebra on this one, or take the inverse log to get rid of log. Or you could actually solve this in our calculator, and you'd solve it in your calculator exactly like we've solved other problems in our calculator. So this one's going to take me a few seconds, so I'm actually going to hit pause for us to spare you the boredom. So pausing now. Okay, plugging this through my Y1 graph and then doing the 0 application there, or command to find out where it crosses the x-axis. I have x equaling 0.622. Okay, so we have to use up quite a bit of our acid, and we have to add quite a bit of base to raise the pH that high to 5.73. All right. Now, you could easily check this, and I'm going to do that very, very quickly. This time I'm not hitting pause, so I'm going to have you listen to me just because I'm lazy. And I'm adding my log, and I'm going to do the actual expression of 0.53 plus 0.622 on the numerator, and I'm going to divide that by 0.74 plus 0.622 on the denominator. And I'm going to get, okay, my answer. Thank you. All right, and my answer is 5.72957, which is going to be obviously 5.73. So our answer checks out. And of course, I know not a lot of us do this, but if you have extra time, if you're lucky enough to have extra time, please put the numbers back in. All right. I know a lot of us do this maybe on our homework with WebAssign when you're on your last attempt. Okay, you should really start to put yourself in that position by doing it on your first attempt. It's nice to know. It's really a good feeling to know that you had the answer correct before you actually click on submit. Okay, it's a good feeling. So how many mLs of my base do I actually have to use? Okay, well this is just going to be the definition of what molarity is. Okay, I'm going to use my area up here for this. Basically I'm asking in order to get 0.622 moles of NaOH, I'm going to need X, okay, times 0.600 moles over liters of NaOH. Doing our math for this, it's just simple division. You're going to get a volume of a little over a liter. Okay, 1.04 liters. So in this case, again, this is the work that's going to go from the previous problem. So my actual answer of how many milliliters is going to be 1 liter, or in milliliters, 1,040 mLs. All right, and that would be my final answer of 0.600 NaOH. There's my final answer for full credit. Okay, so hopefully we see a little bit, these buffer questions are not supposed to be that intimidating, and we want to make sure we're in a place where they're not intimidating. These are technically, usually the pinnacle of difficult questions for AP Chemistry, and hopefully if you see that these are not that intimidating or not that difficult, that's good for you.